start. Convergence and rate of convergence. That is what we spoke about in the end of the lecture last time. What and how do we choose allowable rate of convergence? Okay, we spoke about how many different types of convergence rates? 3. There was linear, quadratic, and something in between called superlinear. In fact, that quadratic, if you remember, there was a square in the denominator, which is why we called it quadratic. You could replace that by any other number. You could make it 3, 4, and it will be 4th order rate of convergence. So the question is, how do we choose? So the bad news is we cannot choose. We come up with an algorithm and do its analysis. It will turn out to be this or that. Okay, it's typically quite difficult to plan to have a certain rate of convergence. You get what you get. Okay. At least the first time when you're doing this. Maybe if you get much more experience, then you can design for a certain rate of convergence, but typically no. Okay. Is it okay to attend this class without any proper concepts of norm, singular value, decomposition, linear algebra? Well, as you saw in last time's class, it may be difficult. But you can take your chances, you can drop it or not. It will be useful if the handwritten notes could be shared. I am not too keen on that. I mean, everything that I am writing is already there in notes form on the class website. Has anyone here seen the notes? Okay, fair number of you have seen. So everything that I am talking about is covered there. So if you want the course, I mean the lecture content, it's there on the website. Go and read it. It's in fully written English sentences, so you can understand it better rather than this hodgepodge which I'm writing over here. By the way, is anyone finding it difficult to follow my handwriting? No one will say yes, but if you do, then write it in the feedback chat at the end of the day. Sir, you should have been a doctor instead or something like that. Okay. Condition number still seems abstract. It will be helpful if it is covered in tutorial. So we will spend a lot of time talking about condition number later on in the course. So we'll get to it. This question I think got asked at the end of the class. For the example we took, xk is equal to 1 by k factorial, we took it in the end. Why is it not linear? Because I can find a r such that xk plus 1 by xk is less than r. And we said that if it satisfies a higher rate of convergence, we just declare it that this is superlinear, even though the question is correct. Then there are a couple of questions about the definition of the p norm. So why is the x infinity norm the maximum value? Okay, so we derived this in a linear algebra course. It's a simple matter of playing around with the definition of p norm. Remember, there's a 1 by p at the end of the expression. You can take that to the left hand side and then take the limit as p tends to infinity. Only one term survives, which is the maximum term. So that's why you're left with it. Okay. Similarly, there's a question that why is the 2 norm of a matrix equal to the singular value? Okay. We would derive this in a linear algebra course. Not here. The derivation is not that difficult. So I won't spend time over here, but if you still find it difficult, I can post a link on Google Classroom for it. Okay, so after speaking about rates of convergence, which is kind of a concept of linear algebra, analysis when we're talking about sequences and what rate they converge, the next thing that we want to talk about is a very important concept of convexity. Now, before we talk about convexity, I want to talk about something a little bit broader than convexity, which is simply how do I combine several points in space? Sounds like a very simple idea. So let's start with as simple as possible. Let's take 2 points. So I'm going to take x1 and x2 are 2 points, and these live in a n-dimensional space. Okay. Further, I'm going to take a couple of scalars which will hang out with these x1, x2. I'm going to call them alpha 1 and alpha 2. They also live in real space. Okay. Now the question is, how can I combine these 2 points? In general, how do I combine n points? Okay, so if I just write this as alpha 1 x1 plus alpha 2 x2, what would you call this? You're giving me the geometry of the combination, which is a line, but in plain English, what will I call this? Linear combination of the points. Exactly. Also abbreviated as LC. Okay. When I made a linear combination of these 2 points, did I have to make any specifications on alpha, on the alphas? No. Alphas can be anything in the real world, right? So that this is the most general combination of 2 points. Now, let's talk about one small restriction. So I'm going to say alpha 1 plus alpha 1 x1, alpha 2 x2, okay, and I'm going to put one constraint, alpha 1 plus alpha 2 equal to 1, okay. So there is now a constraint on alpha, right? Anyone wants to guess what this is called? A line joining. Again, I'm getting geometry. Is there a name that comes to mind of this? Linear combination. This is still a linear combination, but there's something little more special about it. Correct. So this is called an affine combination of x1, x2. Okay. So how would I generalize this to n points or m points? So generalization would simply be sum of alpha I xi and such that sum of alpha I equal to 1, however number of points are there. Okay. Now let's look at one more restriction over here, alpha 1 x1, alpha 2 x2. I'm going to retain this affine constraint and I'm going to add one more constraint, which is alpha 1 greater than equal to 0, alpha 2 greater than equal to 0. Any guesses what this is called? The hint is the first word on the page. This is called a convex combination of x1 and x2. So if I were to draw this, this is my x1, this is my x2, and this is a line running through these points. Okay. So now it's easy to visualize this. When I talk of affine combination, where can the points be? So affine combination means there sum should be 1, but alpha 1 and alpha 2 can be negative also, right? So what do you think is the locus of points over here of the affine combination of x1 and x2? Any point? Or what? Any quadrant. Okay. What is the locus of points that is traced by going through different values of alpha in an affine combination? Ellipse. Any point. What do you think if I tell you consider the red line? So alpha 1 plus alpha 2 has to be 1. So let's take for example alpha 1 equal to 0 and alpha 2 has to be 1 and vice versa, right? So the 2 points x1 x2 are obviously on this, right? If I take alpha 1 equal to half and alpha 2 equal to half, where am I? Middle, right? If I take alpha 1 equal to 2 Is it possible? Yeah, it's possible. For an affine combination, it's possible. Where will I be? Right. So do you agree that all of these points will be still on the line? Right, they will still be on the line. So it looks like I have drawn this line to only be in the first quadrant, but it need not be. I mean, I can extend it like this. Right. So an affine combination basically traces out the entire line on which connects x1, x2. Whereas the convex combination, now you can appreciate, where is the convex combination? It's the line segment between x1 and x2. That's the restriction, right? So this is, okay. So this is just convexity of points. Let's talk about now sets, okay. So how do you think I would define a convex set? Everything is building on the previous step. So I've told you what is a convex combination of 2 points, n points. So what do you think is a convex set? If you were in charge of defining, okay, yeah, go ahead. Correct. So take any points in the set, their convex combination should also be in the set. As simple as that, right? So we can say for any x1 and x2 that belongs to S, their convex combination also belongs to the same set, okay. This is again very easy to visualize geometrically. So supposing I give you something like this. So this is example 1, example 2, right. Example 1 on the left is the convex set, right. I take any 2 points, I can't possibly go out of the set, right. So this is clearly a convex set, and you can see this over here. Although I have some points where the convex combination lies in the set, I am in trouble the moment I pick a point over here, because here I go out, right. Okay, you get the idea. So this is not a convex set, this is a convex set, okay. So like this, there are various further objects that are defined in geometry. You have cones and various other objects, which as and when they are required, we will define. But this is the most basic thing over here, convexity and convex sets. A lot of things that we will do will later on build on this. Okay. Any questions on this? Fine. This is all quite intuitive. You could have defined it yourself. Now let's come to the next important thing, which is we have spoken about convex combination of points. We built it up for convex sets. The next thing is convex function. Right. Okay. Again, a diagram is always helpful to keep in mind. I'm going to take 2 points over here. So a convex function is a function has the following properties. The first property is that its domain should be a convex set. Okay. We already know what a convex set is. Okay. Right. The second point is the really critical point. What defines a convex function is the following must hold true. So what would you prefer? Do you want to know it in words first or in math first? Okay, I'm hearing more math, so let me write the mathematical expression first. So f of alpha x plus 1 minus alpha y. Okay, this is okay. Now, in words, what does this mean? Using the language we have just learnt. The function should be, so graphically it's clear that the function should be below the line connecting the two values, right? That's right. But now, I mean, we just learned how different terminologies for combining points. So what would you call this over here? And I forgot to mention alpha is greater than 0. So what is this combination? Convex combination of x and y, right? So convex of x comma y. What is this entire expression over here? Convex combination of fx fy. So cc of fx fy. So in words, it simply states that the convex combination of the function values is greater than the function of the convex combination of the points. Okay. Okay. All right. So let's take an example of this. So I'm going to write down an expression which we will deal with throughout this course. Okay. So example. Okay, and I'm going to say that A is symmetric, positive, definite. Okay. Now, the question is that is this function a convex function? Okay. Now, when I write it like this, you should automatically assume that x is a vector, right? And in our notation that we'll try to follow throughout the course, wherever you see uppercase letter, it is going to refer to a matrix, right? So, for example, this could be Rn. Therefore, A has to be n cross n. It's symmetric, so it's obviously square, right? What about B? Vector scalar matrix? B has to be a vector, right, of length n. What about C? C is a scalar, right? So, because there is no ambiguity over here, we will not always specify that C is a scalar, X is a vector, A is a matrix. It's evident from here. Now, the question is that is this a convex function? So, there could be like a very rigorous proof of it, and there can be a much simpler casual look at it. So, to look at it, let's just look at the midpoint between x and y. Yeah, question? Does alpha have an upper bound over here? Actually, you're right. Because we're talking about convex combination and the way I've written it over here, there is an upper bound. What is it? 1, right? So, we can write this as 0. Good point. Alright, so let's take the midpoint. That would correspond to alpha equal to half. Okay. Okay. So let's look at f of x plus y by 2. What am I going to get? And what do I need to compare it with? I need to compare it with half of f of x plus half of f of y, right? This is what I need to look at. Okay. So let's open it up, right? So I can combine all the A terms. What am I going to get? Or let's write it out explicitly for the first time. Is that right? Does anything cancel off? What about the C terms? I had a C by 2 and a C by 2 that became a C on the right side over here. I have a C over here. I also have a C over here. So I can knock this off. What about the B terms? Are they equal? Right. So I can knock off this guy with this guy and this guy. Anything else that I can knock off? So let's look at the coefficient of x transpose Ax. On the first term, what is the coefficient of x transpose Ax? 1/2, 1/4, 1/8, pi. One-fourth. Come on, this is not that hard. Half into half is 1/4. And on after the minus sign, what do I have? Actually, I should put a minus sign entirely over here. Yeah, that is. So what will I be left with? What is the coefficient of x transpose Ax in the net? So I have a minus 1/4 x transpose Ax. What about the coefficient of y? Y transpose Ay? Minus 1/4. Is there anything that survives? Sorry, this will be y. Anything else that survives? X transpose Ay, okay. With what sign? Plus 1/4 x transpose Ay, very good, and plus 1/4 y transpose Ay, okay. Sorry, Ax, okay. Can I combine this? So far it doesn't look like something very interesting, but can you see a nice way of combining, making it into only one term with the A sitting in the middle? Very good. So, and what about the coefficient of this combination? Minus 1/4, if I take common, I am going to be left with x minus y transpose A x minus y. Can you confirm that that's all that there is? Look at, so x transpose Ax has the correct coefficient, x transpose Ay also has the correct coefficient. So, this is correct. Does everyone follow? This is just simple algebra, right? We're just moving terms around. And can we say anything else? We are given a special property of A, which is positive definite. That means, what about this guy? Always greater than equal to 0. Therefore, when I multiply by minus 1/4, this is always less than or equal to 0, right? So, what have I got? The function value is always less than the, right? So, the function has a lower value than the convex combination of the function values. Therefore, this is a convex function. Because we proved this is for all values of, for any values of x and y, this is going to hold true. So, this is a convex function, okay. So, this entity over here, x transpose Ax plus B transpose x plus C, is going to appear throughout this course. So, you know, it's one of those characters that you should make friends with. Okay, question? Yeah. Oops, one sec. So the question is, should this hold true for any alpha? Yeah. So this is not a rigorous proof because I just took one particular value, right? You can prove this choosing, taking the full definition of a convex function where alpha should be between 0 and 1. So you should do that proof. I just wanted to give you a flavor of the kind of manipulation that you have to do. So it can be done. It's not difficult at all.
Is it fine if we say a proof says that, let's say we want something which is 1/4, so we can just like half it and then half it again, kind of like that.
You need not restrict yourself to like midpoints of segments. I just took that for fun. You can take any combination. You don't have to assume alpha to be 1/2 or something. You can prove it in general without any difficulty.
If we do like every point should be somewhere in the, like we can just kind of like binary size the point and do.
You could. That may give you a little longer proof. So yeah, this is not a rigorous proof. This is just an illustration to give you practice once again. Okay. So this is about the kind of stuff that we need to know about convexity. So there is convexity in terms of combination, there is convexity of sets, and there is convexity of functions. Okay. So it's very important you don't mix up these three kind of hierarchies, right? And it becomes clear from the context what is being spoken about. Am I talking about a set, a function, or a combination? Okay. Now that kind of completes the review of analysis, and the final thing that we want to review is continuity and differentiability. So calculus in short, right? So this is the third final thing. Calculus, which has continuity and, yes, just one moment, differentiability